I welcome you again for this NPTEL online course on earthquake geotechnical engineering. We are discussing module 3, which is on ground response analysis and local site effects including soil stress interaction. So, we have already discussed ground response analysis, which was the chapter number 1 with 4 lectures, and then we talk about soil stress interaction in next 2 lectures, and local site effects we have the 4 lectures. So, we have already started this local site effect, 2 lectures are already over. Today we are going to have another 2 lectures on the local site effects, that is lecture number 29 and lecture number 30. So, what we are going to talk today in this lecture, in the first lecture of today, first is design parameters which are used for the considering the local site effect, what will be the difference on the parameters. Then what is the one important issue, design earthquakes, that is there are for the design of the structures and facilities, what should be, which earthquake we should use. Then design spectra, then next is development of design parameters, and finally we are going to talk about site specific development, which is also part of the topic number 4, that is development of design parameters. In fact, development of design parameters can be done either using codal provisions or using site specific development. So, let us talk about design parameters. When we talk about design parameter, first before I go ahead, let me acknowledge that this Kramer's book this is a major source for this information which has been collected in this lecture. So, coming to design parameters, earthquake resistant design of new structures and the evaluation of the safety of existing structures will require the analysis of their response to earthquake shaking. So, how they respond when these structures are subjected to earthquake shaking, what will be their response, whether it is for the new structure or for existing structure, it is important. And evaluation of geotechnical hazards, for example, which include the liquefaction and slope failure, will also require analysis with respect to some level of shaking. Now, the issue is this, which level of shaking should we use, for which satisfactory performance is expected, often referred as a design level of shaking, and will be described by design ground motion. So, design ground motion we are going to talk later. So, we need to select the level of shaking that which is which is used for the design of the structures, satisfactory performance during the earthquake. Coming to this point, what is the design earthquakes? We are going to talk in the next few slides about design earthquakes. When we go in the history, design parameters were most commonly determined from a specified design earthquake. So, design you need a design parameters, and to have the design parameters we require design earthquake, and some regulatory agencies still require that earthquake resistant design of structures be performed with respect to the motion produced by the design earthquake. So, you need to select first a design earthquake, and on the basis of the design earthquake the structure or facility need to be designed for that earthquake. The specifications of a design earthquake will implies a level of determination in the seismic hazard analysis, that is we already discussed, which is called SHA, or there are 2 parts of seismic hazard analysis, DSHA and PSHA, we already discussed in detail. In that case, the design earthquake is characterized, either could be deterministically or probabilistically, as we discussed earlier, and its effect at the site of interest are that need to be computed deterministically. So, we can select the design earthquake based on the seismic hazard analysis, which could be deterministic or probabilistic. But once you select a design earthquake, then rest of the things can be done as a deterministic. Continue with that, historically design earthquakes have been associated with the 2 level of design, in which a structure or facility is required to remain operational at one level of motion. So, one level of motion will be that level where even that level of earthquake or shaking occurs, but still your structure or the facility is operational, functional, no issue. And the second is a level of shaking where it may not be operational, but we need to avoid catastrophic failure at another. So, that earthquake comes, but there is no catastrophic failure to the structure. Now, to define design earthquakes, many different terms have been used to describe the level of severity which is associated with the design earthquake, and different organizations may put the different names. Some of the names which for design earthquakes, the maximum credible earthquake, which is in the short called MCE, and this is normally defined as the largest earthquake that can reasonably expected from a particular source. Then you have SSE, what is called the SSE, self shutdown earthquake, which is mostly used in the design of nuclear power plants, and this is maximum peak horizontal acceleration, where the operation of nuclear facility need to be stopped automatically. This is normally done that whenever this occurs, then the nuclear power plants are stopped with its operation. In many organizations, the MCE and SSE have similar characteristics. So, either MC, these are the like the earthquake which is the highest level of shaking, where one can assume to avoid the catastrophic damage. The other terms to use this maximum MC instead of MC which are popular: maximum capable earthquake, maximum design earthquake, contingency level earthquake, safety level earthquake, credible design earthquake, contingency design earthquake. So many terminology are there, but mostly MC and SSE are most popular. So, the two level design approach will require that structure of be designed to avoid catastrophe. The second level is basically to first level is either it is MC or SSE. So, the first level is to design to avoid catastrophic failure at the levels of shaking, and the second one is upper level design earthquake. So, the upper level like you have one side MCE or SSE, on another side you have OBE. So, when we design our facility and structure, they may be designed for MCE in general, in MC and OBE. MC will be maximum credible earthquake, where what we have in case of maximum credible earthquake will be based on that the earthquake where you design the structure, but there should not be catastrophic damage. At MC level, we do not expect that your facility or the structure is operational or functional, but it should not collapse. While at OBE, which is basically operating basis earthquake, at OBE and this is an earthquake where it is expected during the life of a structure. That means, during when the OBE occurs, still your the structure or facility is functional or operational. Normally, the OBE is taken as an earthquake with half the peak acceleration of the SSE, which was the different authors have given different, like Christian in 1988 said that it could be half of the peak acceleration which is taken for SSE, or an earthquake which produces motion with chances are that 50% probability of accidents in 50 years. So, in a span of 50 years, there are chances that this level of shaking may be exceeded, but chances are only 50%, not 100 like more than that. This is by United States called that is a Committee on Large Dams in 1985. Then another like researchers have said that with a retain period of about 110 years, then we said that this is like OBE. So, OBE, but normally like OBE is linked with MCE, and most of the time it is taken half of the MCE, approximately half of the MCE in the simple definition. Continue with this. Other terms that are used for like for OBE: operating level earthquake, maximum probable earthquake, design earthquake, and strength level earthquake. So, for MCE also you have different terms. Similarly, for OBE you have also a number of terms, but ultimately you have two design earthquakes. One is MCE and another is OBE, and these two level design requires that the structures and facilities be designed to remain operational after being subjected to the level of shaking which is associated with lower level design earthquake, that is OBE. So, it should be after OBE it should be operational, but if it is structure or facility subjected to an earthquake shaking which is equivalent to MCE, at that point we may not expect that the structure or facility is operational. However, there should not be collapse, or then there should not be catastrophic damage even at MCE level. So, this was about design earthquakes. Now, the second part that is design spectra based on the design. So, as for the design spectra, there are two types of spectra. One is called response spectra and another is design ground motion. So, the response spectra are often used to represent seismic loading for the dynamic analysis of structure. So, one side you have response spectra. Then design ground motions are expressed in terms of design spectra. So, you have the response spectra, and using the response spectra we prepare the design spectra which will be used further for design. Response spectra can be said like when you carried out the seismic analysis of a structure, what is the response of the structure, that will give you a response spectra, which is normally response versus period or response versus the natural frequency. So, these design spectra and response spectra of actual earth are not the same. That is, based on the response spectra you prepare the design spectra, but they are not exactly the same thing. The response spectra from earthquakes are highly irregular. Their shapes reflect to the details of their specific frequency content and phasing. So, when we prepare the response spectra of a particular structure, which is the response of against a given ground motion, and that spectra is not smooth, but the design spectra is smooth. So, on another hand, the design spectra are generally require quite smooth thing. They are usually determined by smoothing, averaging or enveloping the response spectra of multiple motions. So, here is the answer here, that to prepare the design spectra you use multiple motions, you collect the response spectra from different many earthquakes which may be applicable, and then you prepare kind of envelope, and that envelope will be yielding your design spectra which will be used for the design of the structure or facility. The use of smooth design response spectra implicitly recognize the uncertainty with which soil and structural properties are known by avoiding sharp fluctuation in spectral acceleration with small changes in a structural period. So, it is done, smoothing is done because we want design spectra as a smooth spectra. So, as a result for we avoid the sharp fluctuations which comes in spectral acceleration and due to small change in structure period. So, there is one by Newmark and Hall in 1973 recommended that the design response spectra be developed from a series of straight lines on a tripartite plot corresponding, and this plot tripartite means 3, there will be 3 axes, in fact 4 axes on this plot. So, on x axis you have period, but on y axis there will be split into 3 axes, that is why it is called tripartite plot, which we are going to discuss in detail, which corresponded to acceleration, velocity and displacement controlled portions of the spectrum. And a Newmark Hall design spectrum is obtained by multiplying the p ground acceleration, velocity and displacement values by the factors which are shown in the next table. So, the spectrum for this amplifying factor you obtain the p ground acceleration, and for p ground factors, once you obtain the p the peak values, then these peak values amplifying factor for displacement, velocity and acceleration, they depends on the damping ratio. As the damping ratio increases from 0 to 20%, these factors decreases, while at the same damping ratio the factors value is maximum for acceleration and minimum for displacement. So, for example 2.5, 4 and, but the first line, because you may not have 0 damping. So, let us say I may have 5% damping in the system, then the realistic value will be this one, 20% will be too high. So, in that case the factor which is multiplier acceleration is 2.6, for velocity 1.9 and displacement 1.4. So, using this table one can select depending on the damping ratio the multiplier for this value. Now, as we said that tripartite plot is there. So, let me discuss that tripartite plot first. In this case tripartite plot is shown here. On x axis you have what is called the period, which is in seconds, and if I draw, let us say for 1 second, I like wherever it comes, so it will hit this and then you have corresponding velocity. So, this line will give you the velocity. So, here we see for a particular case spectra, the velocity remain constant between this period and this period 22.8 second in second. So, in this case one side you have the velocity for the same period. If you want to calculate the acceleration for 1 second period, so for the acceleration this axis which is 45 degree should be used. So, the axis for acceleration is this one, this is the axis which is for acceleration in g, while another axis 45 diagonally opposite displacement in inch. So, let us say from 1 second when I hit this here, then I can read the velocity, and for wherever it is hitting, this will be corresponding acceleration axis, and then you have corresponding this is for acceleration value on this axis, while displacement is given from this axis. So, to calculate, like that to have the value of velocity, acceleration and displacement, you will be using these two axes, while for velocity vertical axis is used. For acceleration and displacement, the axes are 45 degree. So, at periods below the continue with this Newmark-Hall design spectrum, what was suggested by Newmark-Hall design, this table is coming from the Newmark-Hall design spectrum. It was also suggested if you have period of below about 0.17 second, that is frequency above about 6 hertz, in that case the spectral accelerations are tapered down to the p ground acceleration, a p ground velocity of 48 inch per second and p ground displacement of 36 inch are assumed to be consistent with Pg of 1g. So, here if you have this below about 0.17 second, for example, the period in this case is even for this velocity is less than 1 second, that is. So, here at this point like is at 0.17 second, this is tapered down and it is tapered down to 0.25 g. So, this tapering is done in case of this because this period is at the tapering is happening at 0.17 second. So, if this is the case, in that case for 1 g acceleration you get this peak p ground velocity as 48 inch per second. So, if so suppose your g is increased, then you need to multiply whatever the g value you have, that should be multiplied by 48 inch per second to calculate the velocity, and similarly to calculate displacement it should be multiplied by 36, and naturally this table should be also used. So, here is one example: develop a Newmark-Hall design spectrum for 5% damping and p ground acceleration 0.25 g. So, here whatever data for 1 g, that should be multiplied by 0.25 g. So, you have 48 inch per second was for 1 g. So, naturally at 0.25 g it will be 1/4. So, this factor comes out to be 1/4, and then the multiplier which is from the table 1.9 for the 5% damping, these factors are 2.6, 1.9 and 1.4. So, for the spectral velocity this should be multiplied by 48. Similarly, for spectral displacement 36 inches for 1 g, and for 0.25 g it will be 1/4. So, this factor is 1/4 of nothing but, and 1.4. So, it will be 1/4 36, 9 into 1.4. So, you get 12.6. Here 12 into 1.9. So, you get 22.8. For acceleration directly you multiply by factor, because for 0.25 g you have 2.6. So, 0.25 g is there. So, multiply by 2.6 give you 0.65 g. So, these are the values of spectral acceleration, spectral velocity and spectral displacement using what we call the Newmark-Hall design spectrum, and these values are at for 5% damping. Now, we continue and how we go to development of design parameters. As far as the development of design parameters are concerned, you have the characteristics, what are the parameters of the design ground motion at a particular site. At a particular site these characteristics will be influenced by the location of the site relative to potential seismic sources, the seismicity of those sources, the nature of rupture at the source, travel path effects between the source and the site, local site effects, and the importance of the structure or facility for which the ground motion is to be used. So, there are so many factors which will influence the characteristics of design ground motion, including the importance of the structure. The manner in which the motion is to be used should also be considered for this. As for development of design ground parameters are concerned, they are developed by two ways. One way is what we call the site specific analysis, and another is called by the from the provision of building codes and structure. The first one, site specific analysis, we will discuss in details. As for the building codes are concerned, these design parameters are already given for the different seismic zones. Like for example, in our country we have 4 seismic zone, and highest is 4th and 5th seismic zone. So, for site specific development, site specific design ground motions reflect the detailed effect of the particular subsurface condition at the sites of interest. You may have some sites of the interest, and those sites of the interest we want to develop, we want to determine site specific design ground motion. The usual process for developing site specific ground motions involves a seismic hazard analysis and a ground response analysis. So, we have one side SHA, on another side we have GRA. So, GRA we have discussed in very much detail, that is one dimensional ground response analysis, or another like two dimensional ground response analysis. So, developing a site specific ground motion will involve this is seismic hazard analysis, where seismic hazard analysis was also discussed as a DSHA and PSHA. The use of probabilistic seismic hazard analysis will require the design motion be associated with some level of risk or return period. Selection of such a quantity can be quite complex. Various social, economic and political considerations are also involved when we develop site specific development. In fact, it would be rather than political, it would be more on the importance of the structure. How big is your project? For example, if you are going to have a bridge or dam, then these are or a hospital, then they are considered to be very important structures, and in that case we use what we call the stringent criteria for the design. So, continue with the site specific development. The seismic hazard analysis, that is SHA, will produce a set of ground motion parameters that may or may not correspond to the subsurface condition at the site of interest. So, normally our target is that they should be corresponding to the subsurface condition at the site of interest. Both deterministic and probabilistic seismic hazard analysis utilize predictive relationships that usually correspond to a fairly narrow range of subsurface conditions if the site of interest is located on a similar profile. So, you have like site of interest is one side you have site of interest, on another side you have a record, the record which has been recorded by the seismograph or the axolograph may be recorded at different site, not at the same site where your site of interest or site of construction is there. So, if both sides have the similar characteristic, in that case the parameters may be then taken directly as the design ground motion parameter. If not, in that case seismic hazard analysis must be modified to account for the effect of local site conditions, and how we can account and how we can modify this design ground motion accounting for the effects of local site condition, we are going to discuss in the next slides. For example, here the parameters modification process may be performed empirically using prior observation or analytically. So, if you have the prior observation, then you can that by thumb rule or that way you can modify that. But in the analytical approach, what we say, both deconvolution and conventional ground response analysis may be required, and as shown in the slide, and this is how it is carried out. I will explain this slide. This slide is in fact in two parts. So, you can say that this is like here rock outcropping motion at CC is there. So, I divide it like this. So, in the first part you are starting from A, B and going to C. In the second part C is common, in both parts C is common. From C you are to going D and D to E. So, this is the way how like you are having. So, let us say the surface motion from seismic hazard analysis is available to point A, and point A is not at the rock outcropping motion, rather the point A is located on a top of a soil column, Below point A you have a soil column, and below the soil column you have the point B, which is called bedrock motion at site corresponding to predictive relationship. Now for this site you have the predictive relationship between A and B. Between A and B you have the soil, but for soil you predictive relationship is known, what could be the attenuation relationship or that is known to you. So what is done, because predictive relationship is known, we use this as a result like characteristics of the site, and using those data whatever the motion given at point A is deconvoluted to find the motion at point B. Now point B you find the bedrock motion at site which is corresponding to predictive relationship. Using that B we determine the what we call the rock outcropping motion point C, and then point C we go to point D, like a rock outcropping motion is known, then we find the bedrock motion at site of interest. And here there is a difference between B and D. B and D are not going to be the same motion. At this point C and point C will be the same, there is no difference at all. But at point B and D, because on the top of B you have some soil cover, its property may not be the thickness, or the properties may not be the same as you have the soil cover above the D. So even motion at point C is same, but still motion at point B and point D will not be the same. So C is common here, and once C is known, then you determine the motion at point D which will have the influence of the soil cover on the top of D. Once motion at point D is known, then we carried out conventional ground response analysis or convolution and find the surface motion of site interest. So we started from point A, this is the beginning, this is the large the beginning, and this is at the E, this is end. So in this case when you do this exercise, the properties of the site between A to B is also involved and D 2 is also involved, soil profile. So these steps are detailed out, and they are like listed here. The seismic hazard analysis will produce parameters that describe a ground motion at the surface point A of a site with subsurface conditions that correspond to those of the site in the database from which the predictive was developed. So that means the motion at point A is given, and the point A is a site with subsurface conditions which correspond to those of the sites in the database which is available to you, where the predictive relationship was developed, predictive relationship between point A and B. To determine the corresponding parameters of the surface of the site of interest, a time history of ground surface motion that is consistent with the predictive is generated. And how it is done? The motion first is deconvoluted. So this is the first step. In the first step, the motion is then deconvoluted through a soil profile corresponding to the predictor to determine the time history of bedrock motion at point A that would produce the time history of motion at point A. This corresponding rock at cropping motion produces the bedrock motion applied at the base, that is point D. So you have this. So this is the first step, and in the second step once you find at point B, then you from point B to point you go to point C, and then finally you go to point. So this will be, so point A to there will be one step, go to point C, and then this will the second step, and in the third step point C to point D, point C to point D. And point C to when you go point D, then the soil profile comes in picture. Then you carried out a conventional ground response analysis. So this is the fourth step basically. So in the fourth step you carried out the GRA. So if I go back, so you can see the first steps, second step. So first is I can write down here. In the first step you go A to B. In the second step you go B to C. In the third step C to D, and in the final step, fourth step, D to E. So using these different steps you carried out the site space development. So, finally, the motion which you find at point E will be consistent with the results of seismic hazard analysis and also with local site conditions, and can be taken as a design ground motion. Because why this can be carried out design ground motion? This will be your final answer, because it will have effect of seismic hazard analysis as well as local soil conditions, and it can be used to compute site specific design parameters such as peak acceleration or peak velocity and response spectra, ordinates and duration. So, thank you very much for your kind attention.